That's done.
Okay. Okay, good. So, good morning. It will be a heavy day for our interaction because we see each other now for this kind of hands-on session, and then we will have a lecture in the afternoon. Okay, so let me tell you two things. I mean, as I said in the email that then the organizer forwarded to you, and also in some message that I put on the Slack, I wanted to use this opportunity to let you use this code that is actually public. Actually, there are two codes. Both of them are related to calculation, of course, within the scheme that we have discussed. So, for instance, with the code that you can, if you had done, that you could have downloaded from my webpage. This is a code which can be used to do just a ground state calculation in Hartree-Fock or Convergence with a Schrodinger interaction. And maybe I will make a run now after I show you how the input is, but also can do calculation of excited state with this theory, which is actually time-dependent Convergence or random phase approximation. It is maybe a bit unfortunate that I will discuss this theory this afternoon, but let's take the pragmatic attitude. I mean, you will do some calculation, maybe you don't know exactly what is behind this calculation, and then this afternoon you will know a little bit more about the theory, but you will have already an example in your computer if you have run the code, okay? So what I would like to do is the following, but as I said, I would like to know whether everybody agrees or somebody has some, I don't know, remarks. I have prepared a few slides in which the detailed input of the code is presented. And I'm going now also to put in the chat the paper. Let me see if I can. I think I can, right? To put in the chat some file. Let me see if I can. Well, otherwise I will do it later, maybe. Okay, I don't know. I thought I could upload a file, but maybe this is not the case with the present. I mean, settings. Okay, in case I will maybe put this this paper on the Slack page. Okay, so I will illustrate input of this code. I will run a typical case. Okay, maybe not the same which is in the paper, so you have a kind of, you know, at least two examples available. And then I would make two alternative suggestions or complementary suggestions. I will suggest you something that you can run yourself, just for exploration, or I will ask you, maybe because of your research interest or your curiosity or your whatever, you want to run something on your initiative and you want to consult with me. Now, of course, I had experience of some similar things when we held meetings in presence, right? So then it was easier because I'm in the room, I say, why don't you run the code? And then I look around at your computers. Now, I ask if you can share the screen. So in principle, we can look at your computers even from a remote, but okay, I never done something like that in remote mode. So I don't know how it works in practice, but I think we should just start and try, okay? Okay, no objection means we should start and try. So let me share the screen now with some initial slides that I wanted to show, as I said. Sorry, where are they? Okay, this file, not this file actually. Okay, I hope you can see it. Okay, so maybe I should better start from here actually. Let me see. Maybe it's better if I do like this. Okay. Okay, so here is a directory in which I did what you should do. So I downloaded the code in my computer. Actually, I downloaded the code in this directory. Well, these are the files that you may already have if you have already downloaded it. So this is just a Fortran, simple Fortran code, which you can compile either with F77 or GFortran or some kind of free Fortran compiler. And then, as you see now, I go in this directory, which is called the lecture, okay? And then I can show you a typical input. Okay, this is a very, very short input, which I will run afterwards. But let me then show you more precisely what is in the input, okay? So I think you should see my slide now. Please interrupt me if something is, whatever you need to ask or to clarify, please interrupt me. Okay, let me also open the chat because this is also useful for people who may raise hand or ask a question. So in this input file, you have a limited number of lines. And in the first line, you should put the name of a Scrum forces, your favorite one, or whatever you like. By default, in this moment, not by default, but if you want to start from something, you can use this SLY5, which is one of the Scrum forces fitted by the Lyon group. So LY stands for Lyon. Also, I mean, the parameters of this functional or force are taken from a file scrum.in. Okay, if you look at this file, there are a list of forces with list of parameters, and you can even dare to add one which is not presently included. And okay, we can discuss this, and maybe you don't know how to input one parameter or you have one doubt. It's a way to go in more detail into these parameters of the forces, but I never discuss in detail in my lecture because I wanted to be more general. Okay, now this is a spherical Conchamp or Hartree-Fock calculation. So it is done by solving the Schrodinger equation with a numeral algorithm in essentially a radial mesh. So of course you will solve for many orbitals which have different angular momentum. So the centrifugal potential of the Schrodinger equation is known by the code, because code knows that it must calculate S1 half, P3 half, P1 half, and so on and so forth. And the integration of the Schrodinger equation is done in a mesh in which you have to specify the step, radial step, and the number of points. In this example, you have 150 points spaced by 0.1, which means the mesh extends up to 15 fairly. You have, of course, to say which nucleus you like. So the third line is just A and Z. This is easy. And then, as I told you in my lecture, then the Conchamp or Hartree-Fock equations are solved by iteration. So it means that you start with an ansatz, which is typically a Wood-Saxon potential, and then you start to iterate, and the code stops when one of these two conditions is fulfilled. I mean, either one or the other. Either the code finds that under two successive iterations, the single particle orbitals have energies that differ less than the first value in this line. So in this case, it's 10 to the minus 5. And then it stops, or it arrives to a maximum number of iterations and it stops anyway, because it means something is not working. So in this case, this number is 300. Okay, the next line is because, well, this is a remnant of tests that we did sometimes in the past. So sometimes we wanted to include or exclude some part of the potential. So in this moment, I would recommend you just include the whole force, the whole functional, the whole mean field potential. But in principle, you could put an option like no Coulomb and exclude the Coulomb part, and have fun to check that if you take a nucleus with n equals z, you get equal levels for neutron and protons. Okay, Hartree-Fock is breaking isospin symmetry in nuclei with n larger than z. Then if you take, you know, a different with a neutron excess and you take out the Coulomb, you don't get neutron and protons with equal orbitals. You may ask why, we can discuss. Again, this is another option. Then you can just end with this line of input file, and the code will just do the mean field ground state calculation. Or you can include this keyword RPA, and then you are obliged to put the next lines up to the last one, which is illustrated in this slide. If you do RPA, you do excited state calculations of a spherical nucleus. So again, this will be in reality explained by myself today, but I'm sure that most of you have already an idea. And even if you don't have an idea, just grasp the simple meaning of this. So you want to calculate an excitation spectrum. And since you have a spherical nucleus, the excitation spectrum is made up with states which are labeled by J and parity because of spherical symmetry. So you will calculate the whole spectrum of the nucleus with that J and that parity. You know that in nuclei, for instance, there are sometimes important low-lying states with 2+ or 3-, and in the region between 10 to 20 MeV, there are giant resonances, which are the ones which I, again, will be discussed again this afternoon, but yesterday already I mentioned the breathing mode, I mentioned the giant dipole, so you will see how these states came out if you run the code. Okay, now when you calculate these modes, actually what do you calculate? You calculate energies, but you want to know which state is the giant monopole, which state is the giant dipole. So you have to apply to the wave function of these states some operator. And then this is specified in the next slide. So I have to go here just for this line number 1, 2, 3, 4, 5, 6, 7, 8. Okay, for this line 8, where you see this 1, 0.6, I go to the next slide. So you will see what are the matrix element square, okay, of between the ground state and the excited state of some operators. If it will be a monopole operator, you will see a prominent state with a large matrix element square, and you will call it the giant monopole. If it is the dipole, and it is Gamoteller or M1, it is the same. So I think that also Robert mentioned some of this excited state in his lectures. Okay, so you have 4 options for this first keyword, which is called IRAD in the code. The simplest option is 1. So these are the operators that you are familiar with when you study electromagnetic excitations. These are operators proportional to R to the total angular momentum with spherical harmonics. So again, J equal 2 will correspond to 2+, J equal 3 will correspond to 3-. These operators will be defined, are defined here in terms of, let's say, mass operator, because they don't distinguish neutron and protons. But in the code, you will have also a column, which I will show you in the output, related also to the electromagnetic case, in which this operator acts only on protons. And so if you have a low line 2+ or low line 3-, you can see the BE lambda, reduced transition probability, that you have seen in your introductory nuclear physics courses. If you take IRAD equal 2, instead of taking the operator with J, you take the operator with J plus 2. If you take IRAD equal 3, then you deal with the special case of the dipole. The dipole is a special case because if you use the simple operator RY10 or XYZ, this operator does not lead to any excitation. It's just a translation of the whole nucleus. Now you want to get rid of this spurious mode, which is not an excitation. It's just a translation of the nucleus. And there are some special recipes to do this that are written, the detailed formula are written here and written in our paper that I recommended to you, I suggested to you yesterday. And okay. I don't know, this is Okay, maybe this is not relevant. Okay, and then option 4 maybe is just for your curiosity. I don't think you are going to use it in the next 20 minutes or half an hour. In principle, you could replace this r to the j with a Bessel function because, as you know, r to some power is just the limit of a Bessel function when the momentum goes to 0. J lambda, for instance, just to use another index of QR for small argument behaves like R to the lambda. Okay, please ask me question if something is unclear. Now I have just the two last line to show you. Of course, so when you do this calculation of excited state, you do it in a basis. So you take into account all the occupied states and unoccupied states. I will come back to it this afternoon, but I'm trying to exploit the fact that Robert yesterday introduced to you, you know, the notation of the whole state, particle whole excitation when he discussed coupled cluster. So if you follow this part, you should be able to understand this. So I'm doing a calculation in which the basis is made up of jumps of particle from below to above the last occupied states. So from whole to particles, as Robert said. And in this case, I have to specify up to which maximum energy I consider this. And the maximum energy is in this case, 50 MeV, is the 50 that you see in the line before the last. And then, you know, if you have a spectrum, you will have many lines, let's say, but with this code, we can also smooth these lines with Lorentzian just to have a continuous curve and show something which is more, you know, okay, nice to see. I have shown to you something yesterday, for instance, when I show the monopole strength, but I will maybe show something again now. Okay, so question about that? Okay.
You have one in the chat.
I have one in the chat. Why don't I see it? Because I don't know why. Sorry, I don't know why I cannot see any question in the chat. Let me see.
Anyway.
Oh, sorry. It's my fault. Sorry. Okay, you explained the one in next slide. What about the 0.6? You are perfectly right. Thank you very much for reminding me. Okay, this 0.6 is important only if you put IRAD equal 4. If you put IRAD equal 4, then you also need to specify this value of Q, and then the 0.6 is the Q. If you use IRAD equal 1, 2, and 3, this 0.6 will not be used. Thank you. Okay, yeah. Anything more? Okay, if not, maybe I try to do what I planned before. So I try to run one case. Okay, so for instance, this is one case which is complementary to the case that I showed you in well, not that I showed you, but that exists in the paper. Okay, so maybe while you start asking questions or you start running things, I will also put on Slack this paper. This is another example in which with another Skirm interaction, which is not SLY5, but with another interaction which is called SKI3, I try to calculate T100. Actually, I remember that in the Gong show, somebody told he's interested in Newton deficient tin isotope. So this is why I was inspired to show this case. Now, how do you fix this mesh? Well, usually you take it 3 times the size of the nucleus, so 4 times or 5 times in such a way that it is, let's say large enough. And in this case, I have taken 20 Fermi with 0.1. This is T100. I have not changed this parameter. I have not decided to take out any Coulomb or do anything special. I do an excited state calculation with 3 minus, and then I'm looking at the option with this IRAD equal 1. Okay, maybe 50 MeV for a basis is kind of small. Maybe you ask me how large this basis should be. Well, actually, the Skirm interaction has a kind of problem because it is a delta force, and because it is a delta force, it does not have a kind of natural cutoff. It is a constant in momentum space. So maybe things converge just because the whole wave function provides a kind of cutoff, but in practice, you better go to maybe 60 or 80 or 100. Again, there are examples in the paper. Okay, let me try to run this. Actually, I have already done it, but let me do it again. Okay. So you run this calculation, and maybe we can start look something like why the code runs. Well, too early. I should give it some time. You can ask questions in between. No, if you just want the ground state, you don't do RPA, right? You just stop and okay, let me show you in this input. Okay, so imagine that you just want the ground state. You don't do any excited state calculation. You take out this, you run like this, you get the ground state. Okay. If you put J pi 0 plus, you also get all the 0 plus excitations up to the maximum energy allowed by your basis. So if you do RPA, the code will do anyway some excited state calculation. Okay, let's have a look. Now there is something to look at. So calculation 14100, this parameter set. So here is just a repetition of your, requesting the input. And then you will see the energies of the proton levels and the energy of the neutron level. The reason why I choose T100 is that you probably, okay. Okay. So there is somebody who is mentioning in the chat. Okay. So in this case, this depends on the compiler. So maybe maybe I should treat this case now. Okay. Let me. Oh wow, too many people. Okay. Let me see if it is. Yeah, it depends on the compiler. But there is also a way to introduce this instruction rewind or backspace. So I know what the problem is, but let me see if I can solve it in real time, or you can try to solve it in real time. The problem comes because the program writes on a file the list of states, and then it reads it again. And then with some compiler, it is not allowed to read again a file if you don't do a kind of rewind. So you go back to the first line. Okay, Francesco recommends to use ifort, and then maybe this solves the issue. Otherwise, I will try to help you on the spot. Okay, so maybe I will continue do something here. Okay, I'm using now. Okay. I think I use G4 on F7. Let me try again. Okay, to me, I think it works. So F77 should be also a good option. F77 is also a good option. Okay. I think in both cases you should be able to. I don't have iFort on this computer, but please let me know if you can download it and if you can use iFort. So when you say you are using gphoton but you can't run, it means that you find the same error that the others found or something different? Okay, good. It works means you can go to the end. I hope so. Okay, let me do in this way. I continue to have a look at the output and then I come back to the questions if somebody still has problem with the compiler. Okay, so what I was trying to say, yeah, I don't know whether it depends on the version of gphoton or the, yeah, it depends also on which computer you are running this, right? Okay. Okay, let me make a simple statistics. So how many people are unable to run the code? One, two, three, four. Oh, quite a number. And you all have this problem with this backspace. Or, yes? Yes?
Gianluca, we had this problem, I remember also with Xavi. I had this, but I sent you an email now because Xavi, when we had this problem, had sent me his version, saying it was compiling with gphoton. And then I don't know because I'm just trying to help you. I don't know if it's
sure.
Maybe Francesco. I don't know. I don't know if it's right because that was exactly.
Yes. Okay. So, but then the question is, but
You could send it
this is
to
another code,
Francesco
the one
Marino
that you
and
are sending.
see.
I remember there was this issue, but I thought we solved it. So
Okay.
now
Sorry.
I think.
I just want to help you, but okay, if you're not.
Yeah. No. Thank you very much. But I think. Okay. Let me see. Let me see if we can.
Yeah, because you just to put one or two lines in the program.
Yes. I have done it several times, but now maybe I don't remember. I'm not able to do it really. Let me see. Okay, so maybe you can check if you have this instruction backspace in your code, which is pretty useful, or I mean, another, yeah. Yes, of course, this only happens if you try to calculate excited state. So, yeah, okay, this is the typical case in which it is very difficult to. Okay, so let me propose to do the following because otherwise we get a bit stuck. I will comment the output, which is something that you can in any case look at, and okay, for the people who have been able to run the code, they can also look at their own. For the other, they will look at mine. And then I will propose to use some exercise, but I will also try to help in real time some of the people who have a problem. If we can, for instance, share the screen and do some kind of debug. I think this is a kind of reasonable options. Okay, so let me continue then with illustration of the output. So I was telling you that my interest in TIN 100 came from the fact that you see output is binary equal even with error. Okay, but then maybe we try to come back to this in any case in a while. After I show to you the output and I also propose to you some exercise, I maybe share the screen with somebody who is finding the error. Okay, so I was saying in the first part of the code, you have proton and neutron states. And then you see this is an interesting case because since the nucleus is neutron deficient, then of course the Fermi energy of the proton is significantly higher than the Fermi energy of the neutrons. Now you have the total energy of the system. You have the radii, so Rn, Rp, and Rc are the neutron, proton, and charge radii. You have also a list of unoccupied states that are used for the basis. So for instance, these are the proton states with S1/2, which are included if you go up to 50 MeV. And then, okay, we can maybe scroll. This part is interesting if you want to have a check on your basis, but does not bring any special information. So the basis is actually made out, as I said, of particle Hall excitation. So you see here what are the particle Hall excitation with 3-. And the physical result is at the end of this long stuff. So you see the excitation spectrum of the nucleus in this J-pi channel. So this is the energy. And this is the quantity that I mentioned before. So the electromagnetic transition probability. This is in this case in E square Fermi to the 6th. So you can convert it into bar if you like. And you have, for instance, here a number for the low line 3-, which has a kind of rather large BE3. And then you have the excitation spectra of the other states, which can be, you know, important or unimportant. At the end of the code, you have also summer rules, which is not something which I explain now because this is not maybe the purpose of this session, but I can come later if you have questions or interest about that. And among the other files that are produced, there is, for instance, these 3 files which are named plot. Okay, so for instance, let's look at this electromagnetic or isoscalar, for instance. Okay, in this case, you have just an energy and the value of this so-called strength function. So you have an idea. So for instance, if I do something like this, okay, and I use this one. Oh, sorry. Oof. I don't know why this is. Okay, maybe something related to the connection. Okay, never mind. You can plot this file yourself on your computer and have a look at what happens. Now, let me do the following proposal. So here are some cases that I wanted to suggest you maybe to run yourself. So you can have a look, for instance, at tin nuclei and, for instance, the ground state and how the single particle states look. Or you can have a look at this monopole and dipole, or you can do, as I said, whatever you like. So maybe the way I'm going to organize it, I will say the people who do not have a mistake and can run the code, they can, you know, just go ahead with these examples or with some other example, and we can have a look together. And for the people who still cannot run the code, maybe one by one, I can try to see if I can help. Okay, maybe I will. It would be nice if we can share the screen and see what happens, if it is possible. I don't know if it is possible that, for instance, Salvatore shows his output. I don't know if you can share the screen and we can discuss this. Okay, take your time. Maybe while this is possible, any other question about something else than the error? Yeah, as I told you, the way I would like to do if we were in a room would be just to jump from one guy to another. But now I don't know how to jump except to see your your comments in the chat. Okay, maybe while I wait, I also put the paper that I promised in this Slack channel. Okay, meanwhile, I have sent this paper in which the code is documented. So you can also have it. Okay, it seems it is not obvious how to share the screen for the others. Okay, somebody, meanwhile, okay, now it seems to work.
Hello.
Yeah, yes, I can see your screen. I can see.
Okay, thank you, great. Okay, sorry, I also had that problem with, okay. So this should be everything we need.
Yeah.
Okay, so if I just try, first of all, for instance, with, okay, in just, yeah, even with F77, it's the same. So, and okay, it does not complain.
Okay.
Then
it should not.
Yeah. And then just
You are running the same example I was running, right?
Well, yes. I mean, it's
okay. Ignore this kind of message that you get there. Is it possible for you, please, to make this kind of, window a bit larger, if possible?
Okay, which one?
The one in which you are writing. So the terminal, let's say.
Yeah. Like that?
Yeah. Okay. And
okay. So that was the input, should be the same.
Yeah. And what about the output?
This is density, and it's empty.
Let's look at the output.
And yeah.
Point out, yes. Oh,
it stops there.
It stops. Are you able to run the example which is in the documentation, so the oxygen 16 case?
But I mean, I just tried the one you.
Yes. You know, it's just to have another example. This is.
You are suggesting to remove this one?
Well, I'm suggesting to, for instance, try another example. Okay, let me see what the problem could be. But you don't get any error, right? You don't get any error.
In the run, this one. In the compilation, nothing.
Oh, sorry. Can you? Sorry, it's a little bit too small for me. But
yeah, let's see if I can.
No, you have a different. Okay, sorry, I said you should ignore this error, but I'm wrong. You should not ignore this. And yes, this is a typical error that sometimes happens, but I thought in this published version it has been eliminated, but probably because of the compiler there is something like this. So yes. Okay, first, okay, let's do step by step. First of all, please remove the line that you have highlighted. So just stop at the ground state. Yeah, exactly. Try to run like this and see what happens. Let's look at the output now.
Yep. Oh, there is stuff now. Well, okay, a little bit more.
Yes, which is a bit strange actually, but yeah, why don't you follow the suggestion of Ilenia, who actually is doing what I was also doing time ago, and I thought it was not needed anymore. So please go to the code, edit the code, go to line 1152. It's very funny because, you know, I had this problem then with some new compiler, this problem did not show anymore, and now it's coming again. So it's a kind of sorry, this makes you waste a lot of time, but this is real life.
No, it's okay. So in the meanwhile, also other people can. So you say line
1152. You can find it in the chat.
Okay.
You can find it in the chat. So just do what these two clever guys did, and I think. But it's nice that you act as a kind of Guinea pig. So now we can run and see. So just do what they say.
All right. Thank you.
So they are better debugger than I am, which is good. I mean, it's good to have a class also for this reason. Okay, maybe one recommendation. I mean, you get an error. Yeah, can you please cut and paste this error?
Okay, perhaps then
No, sorry, I'm just speaking.
Yeah, let's allow her to share her screen, perhaps, so she can.
No. Okay, let me do two things. To Salvatore, please continue like this. Keep your screen open, and we see if the code works. And to David, who put a remark in the chat, please never mind this kind of comment. This is again depending on the computer, depending on the compiler, is a matter of numerical precision. But if the output looks the same as I showed to you, it means the code is okay. So sorry, floating point exceptions are not significant, let's say. So
I'm not extremely super familiar with these inner things of Fortran. So when you say add backspace 9, you just mean to literally paste this thing here?
Yeah, you just cut and paste this instruction. Maybe I I will ask, why don't we do like this? Salvatore, you stop, please, sharing the screen.
Yeah, of course.
And one of the guys who did it, for instance, I name Alessandro because he's the last one. Alessandro Spatafora is the last one. Why don't you show your code and you show your output, please? Thank you very much. So you show to Salvatore where you added the instruction, and then maybe you show your output and we can have some comment together. Salvatore, can you see where the instruction has been inserted? Oh, sorry.
Yeah, I see its screen. No, it's great. Thank you.
Okay.
Thank you, Alessandro.
Thank you, Alessandro. So one suggestion, Alessandro, do you have, even if you answer by the chat, it will be fine. Do you have a tool to make a plot, like new plot or something like that? It's a question to Alessandro or to somebody else who has been able to run the code. The fastest answer will be welcome. Yes, you can use XMGrace. So why don't you do with XMGrace a plot of the file which is called plot underscore is, I mean this one, okay. The file which I was dealing with before. So plot underscore BIL underscore IS dot dat. Okay, try to make it a bit larger. Okay, so what does this thing correspond to? In this nucleus, you have a low-lying 3- excitation, which is around 7 MeV. Okay, and this is the big peak that you see, exactly the first one. And then 3 correspond to an excitation that changes the parity. Okay, if you change the parity, you can just change one shell, or you can change 3 shells. So the bunch of excitation which are between 10 and 20 MeV are those that correspond to the change of one shell. And then you have also higher lying excitation around 30-40 MeV that correspond to the jump of 3 shells. So it's a pretty complicated spectrum. Now, what I would ask you, Alessandro, maybe you superimpose to this plot also the other file which has the same name but with IV. IV is isovector, while IS is isoscalar, and so we can comment the difference between isoscalar and isovector for the benefit of the whole class. Okay, so you see that isovector have a different scale, but definitely isovector is more important in the higher part than in the lower part. So sorry, what did you put in red and green? Maybe you also put the EM, right? Okay, very clear. Thank you very much, Alessandro. So what I want to comment here is that in general, you need more energy to excite the isospin degree of freedom. So on the average, isovector excitation are higher than isoscalar. Why don't we run a simpler case, which maybe can be of some usefulness? Meanwhile, maybe I hope that the other people have been able to solve the problem by doing the replacement of this instruction backspace. Is there still? Okay, let me do like this. I will propose to you another example. So Alessandro, can I please ask you to stop screen sharing and I try to do it myself? Okay, I will propose another example now. Maybe you may, okay, there is something more in the chat. Okay, maybe this is Hannah asked something about plotting. Maybe Alessandro, you can do cut and paste in the chat, and meanwhile I show to the all people another example. Okay. Thank you very much, Salvatore. So, is anybody still having trouble? I hope this is not the case. I hope that this backspace solution works for everybody. But if somebody still has a problem, please write it in the chat. Otherwise, I'm going to show you another example. So let's look at something simpler. Instead of 3 minus, which is a very complicated spectrum with many things, let's try 0 plus, okay? 0 plus. Now, in the case of 0 plus, yeah, by the way, I should also thank you for this very active participation, which is even better than my participation, so that's fantastic. Okay, in the case of 0 plus, you cannot use this operator. Okay, let me show again my slide. Where is it? In the case of 0 plus, you have to use this operator with IRAD equal 2, because if you take 0, it is another special case, the monopole. Y00 is a constant, so it's 1 divided 4 pi. And if you take R to the 0, you get basically no excitation, right? So you have to change this in some way. Okay, sorry, this is not what I wanted to show now. This is not what I need now. So this is also not what I want now. So let me do like this. And let me also run this case. Okay, you can also do the same, by the way. I don't know whose computer is the fastest. This is not so. Okay, we can also do if you want an exercise. Let us try to put 1 here and run the code. Okay, and then we try to run it with 2. Is anybody meanwhile trying to run some other case and finding something interesting or questionable or whatever? You can do, for instance, decide that you are interested in seeing what is the total energy of some nucleus that you are looking at for other reasons, or, Okay, so I'm suggesting to you to run the 0 plus case, and I think you are going to see it in my screen as well. Okay, so you see that if I use this special case, I don't find anything interesting, because I'm using some operators proportional to R to the J, but if J is equal 0, of course, the strength is 0. So I'm not doing anything reasonable, because in the case of monopole, I should have at least R squared. So I realize the mistake. I go back to my code, and instead of having here 1, I put here 2. Okay, I'm trying to mimic a kind of learning procedure, let's say. Okay, now the 0 plus is the monopole. So you are, let's say, welcome to run the monopole and see this giant monopole. And you can also do it in other nuclei, of course. So yesterday, you remember I mentioned somehow the incompressibility and the correlation with the monopole. So I was maybe showing a figure for leg 28. You can also try to reproduce it. Okay, now the code is having some result. So the first part is, of course, the same all the time because the ground state doesn't change. The basis is what it is, okay? And then here you have the spectrum. So we can try to plot the same quantities that we have been plotting before, okay? So anybody volunteers to plot this output if he has been able to run it? I will stop sharing, and if nobody volunteers, I will do it myself.
Maybe Gianluca, might be also be interesting to compare 2 or 3 significant Scherm forces.
Sure, sure. I was going a little bit step by step. But by the way, Enrico, since you intervened, how long do you think I should go? Because of course I could go forever, but I'm not going to do it. So,
I mean, I think there is no problem in going. I mean, in principle, we can have normal timing. So
okay,
you can.
okay. Maybe I
you
will
can
try to finish around 12:30.
Up to a quarter to 1, but then you can.
Sure, sure. Maybe I will finish a little bit before. So answer to Monira, who asked in between. So when you have this problem, it means that you have put some interaction which is not in the list of the interactions. Usually it happens before you because you maybe mixed up some capital letter with some big letter. So do you want to share the screen and show me your input? Mm-hmm. Okay, so can you please show me your input, scrumrpa.in? Thank you, Monira. Just edit, no, sorry, just edit the input file, please. I want just to look inside the input file. So you use whatever editor you like and you open the file which is called scrumrpa.in. Okay, maybe I can, okay, fine. Okay, can you do it a bit larger, please? You put SKI free. You should check that this name, okay, let me, maybe is better if I do like this.
I think she had written SK13 instead of I3.
Ah, okay. You should put capital I and then 3. Sorry, it's too small for me. I'm very sorry. But if you put capital I 3, then it should work. Please try. Okay, I think it should work now. So maybe since you are running the code, I will ask you to volunteer and to show the final strength. It seems you also have a trouble. Okay, probably this is another point in which you need, it's another point in which you need to add some backspace. Did you do it in this line 1152 as the other people did? Exactly as the other people did. You write a backspace. Okay, maybe while you try to solve this problem, I'm asking, is anybody having been able to run this 0+ case and want to volunteer to show the result? Maybe Alessandro is before, but I don't want to force you. While Monira trying to put this backspace 115. Ah, okay. Okay, so. Okay, I will put this in the chat while. Okay, I will. Okay, Monira, I will write this in the chat. No problem if you don't have a microphone. Just stop screen sharing so that somebody else can. Okay, so Monira, I put in the chat. This result. Sorry, not this result. This suggestion. Maybe you try to make the plot, let's say, from 5 to 20 MeV, so it is more visible, the region of interest, maybe from 10 to 30, something like that. Is this the 0+ or 3- case? I think this is... Mm-hmm. Ah, this is oxygen 16. Okay, so not... so oxygen 16 is an interesting nucleus, of course, but the point is a very light nucleus. So usually these excitation spectra are very, very much fragmented. So you have many peaks. So it is maybe better we try a kind of a heavy nucleus. So let's try a nucleus like lead-208 in order to see this monopole more concentrated. So if you stop the screen sharing, I will run this case myself and show it to you. Okay. Mm-hmm. Okay, so let me propose to you then a more heavy nucleus like lead-208. So I still use this SKI3, but you can try, for instance, with SLY5. For instance, an exercise could be to compare two different curve interaction. Then I keep this radial step up to 20 Fermi. Then let's take to replace this with 208.82. This is the calculation of the ground state. I use the again the 0+, and I try to make the basis a little bit larger. So maybe it will take a little bit more to run, but please have a look, ask questions if you like, and try to run this case yourself. Let me look again at the chat. Okay, I'm leaving this. I'm leaving this for a moment so you can have a look, all of you, or maybe even more efficient, I can try to copy this in the chat. Sorry, not here. Okay. Okay, I put in the chat this input that I'm running. Okay, this is the other case. So I invite you to run this case and to have a look at the final distribution of monopole strength. Any other question or any other people who are still somehow having trouble with the various instructions, backspace, and so on? Are there other people doing well with it? Okay, I don't, maybe I should be more specific in my question. Okay, thank you, Monira, for confirming that it works. So since the code takes some time to run, maybe, yes, I want to insist on this first question and then go to another question. So the first question is still anybody having trouble running the code? Okay, it seems at least we solve one problem. Okay, thank you, Diego, for confirming it works. Okay, so as I said, now you could, I mean, either follow my suggestion or try some experiment yourself. Maybe I'm still here for, I mean, I will continue to interact with you for still 15, 10, 20 minutes, something like that. But I want to remind you that it's through the email or through this Slack, I think you can ask me questions about this code and about some specific physics problem even later on, even when after this session is over. Very good question from Salvatore. Ground state expectation value. Yes, so this is the root mean square radius, but you should also find it before in the output. So when I showed to you that you have this Rn and Rp, these are actually root mean square values. So let me show it. Let me show it in my case, and then let me answer to Alessandro. So let me answer to Salvatore and Alessandro one after the other. So first of all, the question by Salvatore, let me show you this. I think you see my screen. When you are in the output, this quantity here, okay, this quantity here are already root mean square values. This is the root mean square values for the Newton, for the proton, and for the charge. The reason why this value look different are two, right? First of all, in this case, the expectation value do not regard the Newton and or protons, but the sum of the two. And secondly, here you don't have square roots. So this 30.92, if you do the square root, this would be a number which corresponds to the mean square radius of both proton and Newton. So it will be slightly different from this and that, although of the same order. Okay.
Gianluca, did you comment also the different energy values in your output?
No, I did not.
Maybe it was worth.
Yeah, I did not, but I will do it now. Let me first, this is a good question, Enrico, but let me answer to Alessandro first and then come back to this. So Alessandro asked how to check if the obtained results for a nucleus are reasonable. Have we checked the obtained radii of other density proteins, and what about the convergence? Okay, first of all, the convergence. Okay, here you have only essentially two parameters to touch, or no, only one for the ground state and two for the excited state. For the ground state, you have just to look at this radial mesh dimension. Now, usually, if you take a well-bound nucleus and you take, you make a calculation in a mesh which is 2, 3, 4 times the dimension of the nucleus, the result should be pretty stable. So try yourself to run only the ground state, so stopping before RPA with a box, I don't know, for oxygen, you can try 15, 18, 12, and you will see that the results are the same. In the case of RPA, there is a further issue because, I mean, again, with respect to the box, the result should be rather stable. But of course, you can increase the basis. Now, to answer this question, I think it is better if I show you the paper that I mentioned before on my screen. So, can you see the paper, Alessandro and everybody? I think so, but okay,
Yes,
just in case.
Yes, fine.
Just in case. Okay, so in this paper, there are already several examples, but you are welcome to try it yourself to get convinced. So let me go, for instance, to this page. Okay, maybe let me move it a little bit down like this. Okay, so for instance, let us take, this is again led to 8 because it's the typical value, right? So your question, Alessandro, is when should I be happy? Or convinced that the results are converged? Well, for instance, this is for a given box, but the box is not so crucial, as I said, provided it is 2 or 3 times the radius of the nucleus. These are the values of the energy of the low line to plus and the transition probability BE2 as a function of this parameter that you put as maximum energy of the configuration. Okay, there is a little thing to clarify to be I mean, more precise. So this is actually the cutoff that you put in the code. I want to make sure that you understand the difference between cutoff in the single particle states and cutoff in the configuration. So you have whole states like -50, -30, up to -10, and you have particle state, for instance, you know, that can be a positive energy up to 10, 20, 50, whatever. So the maximum energy of the particle is the one that you put in your input. Now, of course, when you look at the output, of course, the particle configuration will be much larger in energy because the particle configuration has an energy which is the energy of the particle plus the energy of the whole. So just to clarify again. So this is telling you that if you want some kind of convergence, so you don't care so much about very, very tiny details, maybe 60 MeV are okay. But if you really want a convergence up to a few percent, let's say, or less than few percent, you have to go higher than 100 MeV. And as you see by comparing the left and right plots, the convergence of the transition probability is more delicate than the convergence of the energy. But this plot should convince you that there is a regime in which the calculation is converged. Okay? So this is to comment your point about the convergence. Now, how to check if the obtained results are reasonable? Okay, what does it mean reasonable? It means many things, so let me try to answer at best at your question. So let me take as an example the output that I have just produced. How do I judge that the results are reasonable? Of course, I have to check that the numbers that I get are not completely crazy, so that there is no trivial mistake. So I should recognize that the proton and neutron states are in the, let's say, reasonable range. Then I can also have a look. I can also have a look at the total energy of the system. So this gives me the possibility to comment at the same time your question and Enrico's question. So this is the total energy. So again, in order to check whether my result is reasonable, I can check the binding energy of the nucleus to see how close or how far it is to experiment. And then in the case of RPA calculation, there is another check that you can do in order to see whether the results are reasonable or not, that are the so-called sum rules. So in every reasonable calculation for excitation with respect to some operator, there is a so-called sum rule for the operator. So I don't want now, because I want to leave some room to other things, to explain all the theory behind it, but of course there are in the paper not only some notions, but also some references. So you should see that this number, which is called the percentage of the sun rule, should be close to 100%. And this is close to 100% to a good accuracy. And this means that this is not a crazy result. Then if you plot the spectrum and you are finding some peak more or less with some logic, it doesn't mean that you reproduce experiment. Maybe you are choosing a Skirm interaction which is not at all suitable for this. But yeah, that's another question. If your question about reasonable means I'm not doing trivial mistake, I think this is the answer I would give. I hope this is clear enough. If not, please don't hesitate to ask more. Okay. Other question while we try to understand if anybody was able to run the 0 plus and anybody want to, plot it. Maybe I wait a few minutes for some possible question. Okay, no question. Some question about the output, other things in the output that I did not comment. About the radii or about other properties. Or general questions. Okay, is anybody willing to show some plot of the strength, or otherwise I will do it myself. And then maybe after this we can even close this session. Okay, I will then show something myself.
There are a couple of questions more.
Ah, sorry. I was doing something and not. Okay, fine. Alessandro said it is clear. Thanks a lot. Francesco, may you explain the energy cutoff again, please? Yes. So again, in order to be crystal clear, I will show the paper so that there is no ambiguity in the words, and then I will also answer to Jürgen. So let me do it in 2 steps. Okay. So may you specify the question and cutoff? So please look at the paper that you have, by the way, in the chat here. When you find this parameter dPAP max, so look please at line 9. Okay, so these parameters corresponds to the maximum energy EC, which is also the x-axis in the plots that I showed before to Alessandro, of the unoccupied single particle states, including in the RPA model. So usually I take all the whole states, as discussed by Robert yesterday, and then I go up in energy with particle states up to EC. So if I put 50, it means I take all the particles up to 50 MeV. Of course, particle spectrum should be a continuum spectra, but since I have put my system in a box with a certain dimension, I have a kind of discrete number of states, and I take all the possible L and J states with a maximum energy up to 50 MeV. Now, the comment I made it before, and maybe Francesco, sorry, maybe eventually turned out to be confusing, is the parentheses in this line 9 comment in the paper. So if EC is the maximum particle, then the maximum particle hole energy is EC minus EH, where EH is the deepest hole energy, just to give you an idea of the scale. Okay, so this is what I wanted to say. Okay, so this is regarding regarding the question by Francesco, but if it is not enough, please ask again. And now I come to Julian. If I want to run the code for 224U, which interaction you would recommend? I would say that among the Scrum interaction, there is no, of course, there are, I could send you, if you want, some paper by people who tried to look what happens for very heavy nuclei. And I would say the, for instance, interaction produced by PGR, like this SKI, could be a reasonable choice. But of course, if you go to nuclei which are far from the range of nuclei in which you fitted the Scrum interaction, I think you have to try quite a few and to see the difference between the results. So, Julian, what I would propose is just try a bunch of them and try to have a first idea how dispersed the results are. Okay, are you? I hope this is good enough for both of you. I wait for some more questions, if any. Okay, so I have seen nobody who. Okay, I have seen, yes, no, there is a further question by Hannah. Is it possible odd number of O and Z? No, unfortunately not. This is a code for even nuclei. The reason why I wanted you to run this code, although it has many limitations, spherical symmetry, even number of proton newton, is that the input is also simple. If you look in the literature, there are many codes which are more sophisticated than this one. But I thought that a sophisticated code does not fit a lecture of 1 hour or something like that. There is also a code which is using Scrum functional similar to this code, but which is working for odd nuclei. It is called HF odd, so you will recognize it easily. It is a code made available by also for the public, and you can look for it and download it. Okay, so now I come to the question of Jakub, who says, I try to run 0+ K for nitrogen 14, and I get warning, no square root of 8. Oh, this is a very, very interesting question. So the point is, there are some cases in which, as I said before, an RPA calculation is not very reasonable because there is physics behind the model that we are using. For instance, if you try to calculate a 2+ level and the nucleus actually want to be deformed, the energy of a 2+ level will become imaginary and the code stops. This is exactly what you are finding here. So the nitrogen 14 doesn't want to have the ground state, which is predicted by this Scrum energy functional, and then you find that the RPA matrix has some instability. Now, why don't you try the following thing? This is a suggestion that I can give you, but okay, it's up to you, of course, to try. When I sent the message recommending to download this code, I also said we have a code that includes pairing, which is a code that it is actually documented on the archive, and it is similar in spirit, but also similar in the details. So if you need to learn how to input the code, basically you have already done all the effort. So why don't you try to run that one and you see what happens. Very good. Now I want to share the screen to show my result for this last run, and then we'll see. Okay. So I still remind you, I was working this case. The input for this case was presented by me in the chat. I got this output. And if you have any specific question, if you have run the output yourself, we can discuss it. But then I have also taken this file, okay, the one, sorry, not this five, this one, so the one corresponding to the isoscalar strength, isoscalar monopole strength, and I have made a simple plot with new plot, right? So the result of this plot is this one. I think you all see it. So it's rather actually meaningless to extend this plot up to 60 MeV because the monopole strength is concentrated in some energy here around 14 MeV, and this is an example of calculation of the monopole resonance that I discussed in my theory lecture yesterday, but now the good news is that you could be able to do it yourself. So try to plot this file and you should find the same result. Okay, let me see if there are more questions in the chat. I don't see them.
Maybe, Gianluca, maybe it would be worth at least making a comment about, say, the single particle states that you obtain, because they are part of the output. No, then you use as a sort of, say, just a byproduct, but they are of some importance themselves. I mean.
Yes, okay. Of course, one could say many things about it, but
no, just quickly. But I think it's
quickly,
a part of interesting.
Okay.
Very quickly.
Okay, let me then draw your attention on maybe a few things, maybe 2 or 3, and then of course one could talk longer, but I don't know. Okay, first of all, maybe this is something that I did not comment, and I wonder if Robert commented it, because I followed part of his lecture, but not all of them. I mean, it's true that in many models, including DFT, we cannot give a meaning to all the single particle states, and this is true probably also for other models, but at least in DFT, there is a specific meaning of the last occupied state, so the one which I now pointing with my cursor in both for protons and for neutrons. So the last occupied state should really correspond to the separation energy. So it's not simply a tool to do the calculation, but you can look and try to check whether it corresponds to the experimental proton or neutron separation energy. Most of the Schrodinger interactions do not reproduce this separation energy so well, because of some intrinsic limitation, but there are some who do. For instance, there is a Schrodinger interaction which is called SKX, which usually around the magic nuclei reproduces the separation energy, for instance, calcium 40, 1032, or lead-208. Then, sorry, my terminal is a bit slow. Then, of course, you can also have a look at the unoccupied state. So, yes, maybe I understand the question of Enrico is also in relationship of something that it is a bit transversal to discussion of our lecturers. For instance, I think Antonio Moro will definitely discuss transfer reaction and certainly the fact that if you do, for instance, a DP reaction, you explore whole neutron states, and if you do PD, you explore particle neutron states. So you can also try to see, you know, whether these numbers have any meaning or not. Now, how do you decide this number have a meaning or not? Well, the only number that can have sub-meaning are either the number of negative energy, because they will not depend on the box. So for instance, let's look here, for instance, this list of states, by the way, of course, have a index which is 1 for proton and 0 for neutrons, and then the 3 here correspond to the L, so F, and this is F7.5. So you can try to see whether in the experimental findings, there is indeed some F5.5 level at this energy, and the same, of course, for neutrons. So let me try to do a little bit faster. Sorry, no, this is not what I would like to do. So, for instance, let's look at the neutrons. For instance, I just scroll quickly and I try to find some interesting state. And, you know, for instance, here I'm looking for something. Okay, no, this is not the good output, sorry. okay, for instance, I can have a look whether this energy of a G9.5 minus 2 MeV correspond to something reasonable or not. Of course, the single particle states which are a positive energy, unless there is a kind of high centrifugal and Coulomb barrier that would lead to some quasi-bound state, I mean, this kind of high energy state do not correspond to anything, which are just a basis which is supposed to discretize the continuum. So you should not look at them because they don't bring any special information. I don't know if this is something which is, I mean, either answering your question or interesting for everybody or not, but maybe these are the most immediate comments. Okay, I don't know, maybe my idea is that I wait 1 or 2 minutes if there is some more question or comment, and otherwise I think, okay, I hope you enjoy this session. Can we shoot a glance at the version of with pairing? I have no objection, but I don't want you to you to have no break, basically. So let me do in the following way. Let me do in the following way, Giuseppe. Let me share the screen again. I would recommend to do as follows. Okay, imagine you want to look at the version with pairing. Then what you do, you go on archive. You look, for instance, for me or for my colleague Rocamazza among the author. Okay, you go here, you find this one, user guide for the Hartree-Fock BCS QRPA V1 code. Okay, you look at this entry. Okay, and here you see the program can be downloaded from here and here. Okay, so you download and again you try and you find again some problem with the backspace. You follow what we have found today, right? Then you look at this PDF file and you have some explanation which is a little bit minimal. So minimal means I mean, this short note assumes that you have some familiarity with the RPA, Hartree-Fock RPA case, and you just are interested in knowing how the things are generalized when you do pairing. So there is basically not so much detail about Hartree-Fock, not so much details about this Skirm interaction, but there is some detail about the fact that pairing is introduced by means of some zero-range specific pairing interaction, and there are some detail about the BCS. Again, there is something about the total energy, about the QRPA, and there is an example with the input. So this is also an answer to the question that I was asked before when your colleague told me, oh, I'm very unhappy when nitrogen 14 doesn't work. Please try to do it with pairing, but if you try to download and do this code, you will see that many inputs are similar to the present code. So the first line is the force, exactly as you have seen this morning. The second line is mesh and step, exactly as you have seen this morning. So there are some differences, but also many similarities. Maybe I should spend only 1 minute on the differences, on the specific things. So the specific difference are maybe this one. Because this part and the last part is similar to the previous code, you can decide yourself that you activate the pairing in some automatic way, or you do it by yourself by choosing the input. If you do it automatically, you just put sorry, 0 here, 1 if you want proton pairing and 1 if you want neutron pairing. And then you don't have to do anything more. If you want to do it by yourself, you have to specify how many levels you want in the BCS calculation, so you need to specify a few more parameters. If you run this code and you have a question, please do not hesitate to ask. The rest is similar to what we did. You see that also the output is pretty similar, and there is again here an example. So if you want to go in this direction yourself, I would suggest again that you download the code, you check that with G4 or F7 heaven you have no trouble, you reproduce this example, and then you try, as your colleague said, I don't know, nitrogen 40.
But Gianluca, in general, it's not guaranteed that if you have a calculation does not converge when you do it in simpler code, it will converge.
Yes, of course. So this is
not converge, better, can be run. Sorry.
Maybe
no,
I was a little bit, how can I say? Well, I don't know, maybe I didn't insist so much, but the key point is that, of course, when you run these codes, you are not guaranteed that you get a reasonable result, because as I said, if you try to calculate with a spherical code a nucleus which is heavily deformed, or if you try, to calculate a nucleus that is very far from this simple Consham description, you may find trouble. But at least you can, I mean, is apart from the time, I mean, it is maybe if you want today in my theory lecture, I will try to, in the conclusion, to tell you a little bit more about the limitation of what I am discussing, and also the limitation of the specific codes. But it would be somehow, how can I say, difficult now to do it in a few minutes. Of course, every code corresponds to a model, and every model can be applied in certain cases and not in others. So, of course, you are not guaranteed. But what I can say on the, let's say, optimistic side is that if a code stops and you need to understand why, in general, you learn much more than if everything goes smoothly and you produce a curve that already exists in the published papers. Yes, I don't know if this silence means that we should stop.
Yes, I think it means that
I think you need some break, but I also need some break, because we are going to meet again at 2:30. So
yes, we have to preserve the speaker.
No,
So
no,
thank
no.
you.
I'm perfectly fine, but I'm